All right, we should get started. It's about time. It's already 3:10 or 3:11 even, almost. Okay, so let's get started. All right. So, well, let's see. We're on the other end here, the other side of PA6. So, hopefully, most of you have submitted it by now. Okay. Yeah, and I hope it wasn't too bad. All right. I don't think it should have been too difficult. There was, like I mentioned before, that there was just some weird stuff. The environments were generalized to hold expressions instead of values. Okay. But other than that, it's pretty straightforward. All right. And we had started on Friday talking about this idea of unification. Okay. And while constraint-based type checking as another way of doing type checking, but at the core is this kind of general algorithm called unification for kind of finding solutions for sets of equations, basically. And then we can take unification and apply it to the problem of type checking with type inference. Okay, so that's what I want to do today. Okay. This is our only day for this week, I guess. So I'm just going to start by kind of reminding us, doing a little review of what we did Friday, and then we can look at the unification algorithm, and then we can see how to apply it to sort of like polymorphic scheme 1. We can extend the type system of scheme 1 to support a certain kind of polymorphism. Okay. So let's go ahead and remind ourselves what we did last time. Let's see. Well, we had this idea of a type substitution, okay, which I usually denote with sigma or sigma something. Okay, so a type substitution is just a mapping from variables to types. That's one way to think of it. Or you could also just think of it as a function from types to types. So if you've got a type substitution sigma and some type t, then you can apply sigma to t. And that'll be a new type. That is the result of performing the substitution. Okay, so we can kind of think of these as just like type transformers. It's a function that takes a type and gives you a new type. Okay? And so because of that, I mean, you can compose substitutions. Okay, you can take one substitution and compose it with another, and that's like just saying, well, do one substitution and then do the next. Okay, you can kind of like thread them together in sequence. Okay, we looked at a couple examples here. Like suppose here, this is our sigma, a substitution, and it maps x to num and y to bool. And then suppose we have this type t that's x or y. Well then, when we apply sigma to t, we would get num arrow bool, because you just performed the substitution. All right, and then okay, and then that's when we get to unification, because now the situation is that, well, suppose you've got just some set of equalities. These we call them constraints. They're equality constraints, where you just have like some type is equal to another type. But you have a big set of these equations that look like this, where the types could contain type variables. Okay. So the unification is an algorithm to find a solution for a set of equations like that, where the solution is a type substitution. Okay. So here, a type substitution sigma is a solution for a constraint set C if when you apply the substitution to all the types in the constraint set, then all the equations just become identities where both sides are literally identical. Okay? So if for every Si and Ti in an equation like that, you apply the substitution to both, then the two sides will be identical. So whenever you've got a substitution like that for the constraint set, we say that it's a unifier for the constraint set. Okay, so unification is about finding a unifier. Okay, so the input to the unification algorithm is a constraint set. And the output is, well, it'll throw an error if it can't find a unifier. Or it will give you a unifier, which is a substitution. That is a solution. Okay, but it doesn't just find any old unifier. It actually finds the best, or the most general one. So let's just look at an example here. Add a new page. So I'll write down another example. Suppose we've got a constraint set that, this is a really simple example, that is like x arrow y should be equal to z arrow w or something. Okay. So now what we want to do is find the most general unifier for this constraint set. Well, it only has one constraint, and so there's some things that we could choose that would unify this. So technically, suppose we map x to num, and y to num, and z to num, and w to num. Okay, so then this would unify the constraint set. If you apply this to C, then you would end up with just num arrow num equals num arrow num. Okay, so this is a unifier. But here's another unifier that's better. Okay, how about we map x to z and y to w? Okay, this is also a unifier because when you apply it to C, you'll get z arrow w equals z arrow w. Okay, and that one's better because it's more general. Okay, it's less specific. It unifies the constraint set by doing kind of as little as possible in a way, and it leaves it as general as possible. So this is the principal unifier here. I don't think there's one that's any more general than that. And so the way to kind of formally state that is that any other unifier you could obtain by first applying this one and then doing another substitution. Okay, so any other unifier can be factored through this one if it's the principal unifier. Okay. All right, and then we're going to see that we can use this technique of kind of generating constraint sets and using unification to solve for the principal unifier, the most general unifier. We can use that. We can apply this to doing type inference. Okay, first, let's look at the actual unification algorithm. All right, because it's not too bad. Okay, so unify is what I'll call it, and it takes a constraint set, which I suppose. Each constraint is just a pair of types, right? Because it's just an equality. We're saying, well, this one should be equal to that one. So you could store it as a pair. So if you wanted to come up with a type for this, it'd be like list of, I don't know, don't really want to use pirate syntax, but if we wanted to, it'd be something like this. So that's the input to the unify algorithm. It's a list of constraints. We can do it that way. And it gives you a type substitution, which you could represent as a function from types to types, right? Maybe I should write this a little bit differently. Okay. So maybe when we get to implementing it in code, it has to be kind of like this. But for now, let's just say, the input is a set of constraints, of type constraints. And the output, a unifier for C, okay, which is a type substitution. The unifier is a type substitution. So, because I want to write this in just kind of general pseudocode that's not really specific to Pirate, right? So let's go ahead. So say unify of C equals what? Well, let's see. If C is the empty set, okay, if there are no constraints, then we just want the identity function, okay, for the unifier. So, remember, if you think of substitutions as functions from types to types, then the identity function, which just, returns its argument unchanged, is technically a type substitution. It just doesn't do anything. Okay, so if there are no constraints, then there's nothing to do for the unifier. Okay, else, if there are constraints, then let's pull one out. Let's say, I'll write this. Let's say here's the constraint, s equals t, or the syntax is weird, but let's break up C into, s equals t union C prime. So we're saying, well, so if C was not empty, then we can pull out one of the constraints, and it'll have this form s arrow t, and then C prime is like the rest of the constraints. Okay? So let's do that. Just pull out one of the constraints. Okay? And then we have some cases to consider. Okay, so first of all, if they're equal, okay, then there's nothing to really do. It's kind of the constraint is trivially satisfied already because the two sides are already equal. So let's just continue on with C prime. Okay, so there's nothing for us to really do, but let's just take the rest of the constraints and unify them, and that'll be the result. Okay, else, and here's where it's a little more interesting. Else, let's take a look at s. So if if s is a type variable that I'll call x, then there's something we could do. Okay, but that's not the only condition. Let's say if s is a type variable x, and x is not in the free variables of t. Okay, so I'll get to what this means in a minute, but there's this extra condition where we say, well, so if the left type, if s here, is a type variable that doesn't appear in the right-hand side, okay, then we can do something. We can do a substitution. Okay, I'll write it like this. Then the result will be, well, map x to t and compose that. I wrote that wrong. Did I write that wrong? I think I made a mistake in my pseudocode. Let me double check. In the book. Got the algorithm here. Yeah, okay. This is right. And we'll compose that with something else. So I'll have to unpack what this means a little bit. Okay. But essentially we're saying, well, if the left-hand side is a type variable, then let's go ahead and let it be equal to t. Okay? Got this extra condition too, but ignoring that for a second. So we're saying that if the left-hand side type is a type variable, then let's go ahead and map that to the right-hand side. We say, okay, let's let x be equal to t. We're going to do that as part of the substitution. Okay, so right away that becomes part of our solution. It's okay, map x to t, and then we'll have to do the recursive call to get the rest of the substitution. But instead of recursively unifying only C prime, we also go ahead and apply the substitution to C prime. So that if x appeared in any of the other constraints, well now, it's t there instead. Okay? But this is all we're doing really. It's just if the left side was a variable, then let's map that variable to the right side. Okay? And do it everywhere. All right? And then there's a symmetric case. Well, I guess I'll put else if here. Else if t equals a variable x, and x is not in the free variables of S. Okay, this is just a symmetric case for doing the same thing. But where the right-hand side is a variable, so we're going to map that variable to the left side type. Okay, and we'll do it everywhere. We do it in the solution and also in the remaining constraints. Okay? And then there's one more. So if neither side was a variable, there's another case to consider, which is when they were both arrow types. Okay? So if S equals like S1 arrow S2 and T equals T1 arrow T2, then what will we do? Well, we'll just constrain S1 to be equal to T1 and S2 to be equal to T2 and continue unifying. Okay, so we're just going to recursively unify C prime with some additional constraints now, saying S1 equals S2, or T1 I mean, and S2 equals T2. Okay? So it's like just record some extra constraints now for the two sides and continue unifying them. Okay? And then one last case, else fail. So if we get to this point, then we can't unify. Okay, so we might get here if like S was an arrow type and T was not. Then you'd end up hitting this failure because you wouldn't be able to. Well, and T was not a variable. Really, if T was a variable, then you'd hit this. But if T was like num and S was an arrow type, or if T was num and S was a bool or something like that, or was bool. Okay, then it's possible to fail. But this is it. This is the whole algorithm for the language of types that just has arrow types that we're using. Maybe it has num and bool or something, but but that's it. Okay. So if we had some extra types, like suppose we had pair types as well, like product types, then there would be an extra case for those that's found the same thing as for arrow types, where it's sort of like a congruence case, where you're just kind of pushing the constraints down into the subparts of the type. But anyways, this is it. Now I skipped over the free variables thing, and this is to prevent cyclic things. So consider an example. Suppose we had a type constraint that looks something like x equals x arrow y. Okay? So the left-hand side is a type variable x, and the right-hand side is an arrow type where x appears. Okay? So if you didn't include this check here, x being in the free variables of t, then you would generate from this constraint a substitution that looks like this. Okay? And this is a bad kind of thing that you generally want to avoid. Okay? Because it's sort of like, it doesn't actually get rid of x, and it's like a cyclic substitution. Okay? So this is called the occurs check. When you check for x being in the free variables of the other side. Okay, so one interesting thing I mentioned before, the Prolog uses unification, kind of at the heart of how it performs computation. And most of the time, though, the implementations of Prolog leave out the occurs check, just for performance reasons, because it's kind of expensive to have to compute the free variables of an expression at every step of unification. So just as a performance hack, essentially, they'll leave out the occurs check. And that means that you can get these infinite loops in Prolog, and it's really nasty when that happens. You just have to be careful not to write Prolog programs that do that. So anyway, but we'll include the occurs check because we don't really care too much. Right, so one thing, how much time do we have? Okay. So I guess I want to get to a little bit of code, I suppose, to see how we can apply this. Okay. But this is it. This is the algorithm, and I mean, maybe it's not immediately obvious why it works, but this computes principal unifiers for constraint sets. And also, it's maybe not immediately obvious that it terminates, that it's guaranteed to terminate, because there's like this step in particular that is sort of like adding new constraints, you know? And so you can imagine maybe that when you try to run this, that you could like just keep hitting this step and it would like add new constraints every time. Okay, if that doesn't happen, this algorithm always terminates, right? So that's pretty cool. All right. And so now, okay, let's take a look at how we can apply it to type inverse. So let's take a look. So what I've done here is I've taken our type scheme 1 language. Here it is. And the first thing I've done is remove the type annotations from the syntax. So now, like let expressions, oh, whoops. I actually need to remove them. Okay, I removed them in the abstract syntax. But so the idea here is to take out the type annotations. That's the first thing. And the second is that let expressions are no longer desugared. These are not going to be a derived form anymore because we're going to have some kind of special behavior for let expressions. So now you can no longer desugar let expressions to function application because of this extension that we're making. Because we're adding what's called let polymorphism. So in let polymorphism, let expressions are special. Okay? Is that the things that you bind with let expressions are the only things that can be polymorphic in this language. All right? So we've done that, and we've updated the parser so that it knows how to parse the new syntax. Just gotten rid of the type annotations, okay, and updated the desugarer and is core. Now let expressions are considered core. Oh, I guess it should recursively check the. Well, let's just ignore that for now. That's actually wrong, right? That's fine. You get it, right? Okay. Sorry, I mean, I hacked this up last night, so there could be bugs. Right, so the parsing, okay, not really the interesting part. The desugaring, not very interesting, but now, let expressions they stick around, and we just recursively desugar the parts. But here's where we get to the type checker. So the real thing here, first of all, let's find the type check function. Here it is. So first of all, here's type check, and it's kind of the same as before, except the environment now, instead of types, is this thing I'm calling a type scheme. So we'll look at that next. Okay, I forgot about that. But it's essentially the same thing. It's a type that might be polymorphic, is what a type scheme is. Okay? But the real thing to notice here is that the result type is no longer just a type, but it's a type and a constraint set. So perhaps we'll look at what these types are, what type scheme and constraint set. This is just a list of constraints. Okay? So constraint set here is just like a list of pairs of types. Okay, that encodes equality constraints. All right. And the strategy now for type checking, which I alluded to before, is that this algorithm that is very much similar to the one that you've written already. I mean, it may or may not have looked exactly like this, but you just recursively type check the expression. But what you're really doing here is just building up a list of constraints. Okay, this is constraint generation. And that's what this part of the algorithm does now. And so then at the end, you've got, well, let's take a look. This is the real overall function now that takes an expression and gives you a type. And what it does is it says, well, build the list of constraints by calling this tycheck function. You'll get a type and a set of constraints back. Okay? And then unify the set of constraints, which will give you a substitution, sigma. Okay? And then you'll go ahead and apply that substitution to the type. And that will be your type at the end. So this is the new strategy for type checking. It's just constraint generation followed by unification. Okay? So that so this part of the algorithm now, instead of actually checking that types match up as it goes along, it just records constraints for later consideration. It'll say, okay, well, we expect these two types to be equal. But we can't necessarily check that that's the case right now because they could have type variables in them. And so let's just record the fact that they should be equal. And then later on, we'll have this big set of constraints that we can try to solve using the unification algorithm. Okay. So let's go back up and look at the types of things that we're using. We've still got time. Okay. So I'm saying a tie subst. This is a type substitution. It's just a function from types to types. Okay. And then the kind of simplest one that you could build is just mapping a single variable to a type. Okay. So if you call subst here with a string and a type, then it'll give you a type substitution that just performs that single substitution. Okay, so this is kind of like the basic way of building substitutions, and then you can get more complicated ones by just composing these together, right? Yeah. Right. And maybe I meant to write something here because
Does unifying the constraints essentially give us a better type checker?
Well, so there are pros and cons. I mean, mostly yes. The only con really is that it can be that the type error messages that you get whenever unification fails are sort of less localized. Because like before, it was a lot easier. You could tell exactly where the type error comes from, and you could spit out an error message to the user that right then and there, like this is in the spot in the code where the types didn't match up. When you do this, you're building a big constraint set, and then oh, the unifier fails. You don't really know why necessarily, and it's trickier to keep track of things. But other than that, it's pretty much just better. This is really at the basis of like real type checkers, right? Pirate uses unification. Most like
everything else like C++, Python.
Well, they may or may not. I don't know because they have pretty simple type systems. But at least the functional languages that have type inference, they're unification based. So, this is kind of more like a real world production level type checker. Okay, of course they may have some extensions and make it more complicated, but this is the basis for it. There's one thing I meant to include here that I don't know, just because I use this notation. I hope that you've seen it before. But this little circle for function composition, and that's just in general, if you've got two functions f and g, then you can write this as their composition, and you pronounce it g after f. Okay, and it's just a new function that if you apply it to something, it's just g after f applied to x. This is function composition, just in case that wasn't clear. Okay, so that's why if you have two substitutions, f and g, you can compose them like this, and it'll just be something that takes a type and does one substitution and then the other. Okay, and that's why here we only really need to implement a function for doing a single substitution, and then you could build up bigger ones by just composing these. Okay. Right. So then here, a constraint set is a list of pairs of types. Okay, and there's some other stuff here that isn't super important, just kind of bookkeeping. Okay. Here's free variables. It takes a type and gives you a set of strings. And whenever it sees a variable, it creates a singleton. And when it sees an arrow, just it takes the union of the free variables of T1 and T2. Okay, that's pretty easy. All right. So here's the type scheme thing. And the idea here is just that we're committed to prenex polymorphism. So if you remember prenex, whoops, it just means that all the quantifiers are all the way to the left-hand side. So you can have things that, you can have polymorphic types that look like, for all x, for all y, etc. But all of these for all quantifiers are all the way over here. Okay, and so we can represent polymorphic types like this, where it's just a list of the quantifiers. I'm calling tie bars here. Okay, and then a type. Okay, so this is a prenex polymorphic type. And of course the list could be empty if it's not polymorphic. Okay, and so we're just calling it a type scheme. All right, and there's some functions here that I'll skip over for now, just for manipulating type schemes. Okay, but I just want to cover kind of the high-level idea of how this works. So let's take a look at some examples here. So here's the function for type checking a unary expression. Okay, it just takes gamma and the unary expression or the unary operator and the expression e, and it gives a result of type and constraint set. And how is this working? I suppose you don't necessarily need to do this, but it makes sure that we've got a u0. And then what it'll do, it'll recursively type check e, and what you get back from doing that is a type and a set of constraints. So it's like these are the constraints that were generated from type checking e recursively. Okay, and then here's the type of e. And then we'll return, well, t bool, because that's going to be the type of our u0. It's always t bool. And then a new constraint set that is these ones, we have to include those, plus something else, which is constraining the type of t to be bool. Right? So if you remember, what you would normally do here, you would recursively type check e, and then you check if its type is bool, and if it is, then you'd return OK bool. Right? But here, we're not doing that. We're just recursively type checking it to get its type and a constraint set, and then we're going to add a constraint to say, well, we expect that type to be bool. But we're not actually checking it here. We're just recording it for later consideration. Okay? And that's unext. And they pretty much all work the same way. How about for binexp? You've got the binop and E1 and E2, and we'll recursively type check E1 to get a T1 and a constraint set for that, C1, and then we'll do the same thing, recursively type check E2, get a type and constraint set for that. And then I've got this little helper here for saying, well, is it one of the binops that has a t-num return type, or is it one that has a t-bool? So we'll use that to choose the type here. And then the constraints will be, well, all the other constraints that were generated, plus a couple more, because we expect T1 to be a num and T2 to be num. Okay? So, this is constraint generation. And they all kind of work like this. Okay, and they're mostly straightforward. So I'm not going to spend a whole lot of time on that. Okay, but then the interesting case is let. If you recall, there's special behavior now for let expressions. So let's see what we do here. Okay. So let, again, it takes the variable name E1 and E2. You're saying, let x be E1 and E2. And we'll start off by type checking E1 to give us a T1 and a C1. Okay. But then, before we move on, we're going to go ahead and try to unify C1. Okay, so we're using unify here. And I haven't showed you the code, but it's just, I showed you the pseudocode. So this is just an implementation of the pseudocode for unifying. And it'll give you back a type substitution that's a unifier for those constraints. Okay? And then we'll go ahead and apply sigma, the unifier, to the type. Okay? And then we're building a type scheme out of it. So it might be good to look at examples here. Let's think of an example. I am running out of time. Okay. But the idea here is that if you so if you unify the constraints and then apply the unifier to T1, and then you look and see, well, are there still any type variables there? So it turns out that if there are still type variables remaining in T1 after applying the unifier, then what that means is that T1 doesn't care about that type, whatever it is. Okay, there's some type variable there that's left open, and it was like, well, none of these constraints actually constrained it to be anything. Okay, so that, you know, basically E1 doesn't care if that type is num or bool or anything. Okay, and so what generalize does is it just looks for free variables and pulls them out and builds a type scheme where those type variables are considered to be polymorphic or type parameters. So let's take a look at an example here. So say we have a program that is like let f be, you know, fun xx. The first simple example here. Well, you know, in, and then we'll apply it to something f0. Okay. So what's our algorithm going to do here? The constraint generation. Well, we're going to recursively type check this. And what this will do, well, it'll give us no constraint at all, actually. So it'll generate, the type of it, it's going to look something like this. Okay? That the type you get back from type checking this and then unifying the constraints, there will be no constraints at all. And so then when you apply the unifier from that constraint set to the resulting type, it doesn't change it. And it still is XROX. So it's like after applying the unifier, there's still a type variable in there. And what that means is that this function didn't care what this type was. Okay? And so this generalized operation just looks through the type to find the type variables and turns them into quantifiers. Okay? And creates a type scheme out of it. And so this is how we've gotten this polymorphic type for the function here. It was because, well, nothing inside the function constrained this type variable to be anything. Okay? And so since we found the most general unifier, the one that kind of does the least, well, it left that type variable there, and so we know that we can generalize to make a polymorphic type out of it. Okay? So that's what we're doing here, where this is where the polymorphic types come from. Create a type scheme, and then you'll go on to type check E2 under an extended environment where you've included this type scheme. Okay? And everything else is normal. Okay? So then the only, the other part to this is when you look up a type scheme, when you find an identifier. So when you're type checking an identifier, then, well, you can look up the identifier in Gamma to give you a type scheme. Okay? And then you'll instantiate it. So what does instantiate do? Well, it'll take a polymorphic type that looks something like this and go ahead and just generate some new, never seen before type variable that you might call like x, who knows, just some number, okay? And substitute that in for x. Then you get like x23. Okay, so it'll generate a new type variable, a new fresh type variable that's never seen before anywhere, and substitute it in for x, and give you a type that looks like this. Okay, and then let that be the type. So that's what this is doing.
So that's like an alien type? Never seen it before?
It's fresh. Well, the type variable is fresh. So the idea is that if we want to instantiate this, then let's go ahead and just kind of create a new type variable and substitute it in for the quantifier thing. So we'll take like, we'll just say it was like x23 because maybe you've got some counter that you're using to keep track of. So then, you know, next time it'll be x24. So you can always generate a new one. Okay, and then you'll go ahead and substitute that in. So now, now its type is this, and it's sort of free to be unified with something else. Okay, so then maybe x23 ends up being unified with num if you're using this function and passing it a number. Okay, or if you're using it with a Boolean, then it could end up being unified with bool. But that's the idea of instantiating the type scheme. And that's it, okay? And we are using, there's a thing I found that's actually built into Pirate. If we look at this instantiate function, I made this fresh tyvar, okay? And all it does is it just creates a tvar, and it uses this built-in primitive in Pirate called gensim. So gensim, all it does is it has a little counter variable internally, and then you can pass it a string, and it'll give you back that string with a number at the end. Okay, and every time you call gensim, it'll be a different one. And so, I don't think there's any documentation for this, but I tried to make one myself, and there was some naming conflict, and figured out that they've got one that you can use already. So, and actually, you know, they're using this in their type checker. So every time you call this, it'll be some like huge number, and it's like different every time because, you know, they're actually using this for internal type checking stuff because they're doing the same thing. Okay. Now, it would be good with the remaining time, we've got a few minutes, to look at some examples here. Something simple. Let's comment out some of these. What do we want? Well, we need a let example. I'm running out of time. I want to make this print out the constraint set. So when we call this tycheck unify function, let's make it print C, print new line, and okay, we'll run one case here, one test case, and have it print out the constraints that it generates. Oh boy. Suppose I can make a smaller example. Let's make a smaller one. It'll be this identity function, and we'll apply it to 0. Alright, it's going to complain that it's not the same, but okay. So what are the constraints here? We've got this list of constraints. And it ended up looking like this. It says T arrow of T bar with some fresh thing, or question mark x109. Okay? And then it's the same one here, x109. And that should be equal to T arrow T num, and then some other type variable, x110. Okay? So when you pass this constraint set to the unifier, the unification algorithm, I mean, then it'll give you back the principal unifier, which, you know, it must map 109 to T num. So then 109 becomes T num everywhere, and then it also must map 110 to T num. So whatever the unifier is, it must be the one that maps both of these type variables to T num. Okay? And the reason for that is because we're doing this. We're applying it to a number. Let's try applying it to a bool instead. And I expect it should be pretty much the same, except we'll see T bool here. Yeah. And of course, we've got different numbers from the gensim counter, but now it's T bool there, and so the unifier will all become T bool. Let's see. I kind of want to. Let me go ahead and just give it a function only, funxx. Of course, this test will fail. It's not going to be equal to that, but it should still print out the constraints. So let's see what we get from just type checking this potty. All right, there's no constraint, right? Because you know, it doesn't care what x is. But let's do something a little more interesting. Let's say, what if we say plus x1? Running out of time, of course. Let's give it a shot. Now, what is the constraint? Well, you can see that it's going to constrain this type variable to tnum. Okay. And so now, after doing unification, there's not going to be any type variables. And so when it tries to generalize, it's not going to be polymorphic. So this function is no longer able to be polymorphic because it now cares about the type of x, because it's using it in the context where a number is expected. So it's going to constrain it to be type tnum. Okay. So we could, just for the last couple seconds, there's some examples here. Like here's a little example program that defines a double function. The double function is this function here that takes a function f and a value x and applies f to x twice, right? So if you think about this, it shouldn't actually care what the types are. Okay, this could be a polymorphic function. Okay, and then, well, we're using it here on we're saying, well, let g be a function that adds 1 to its argument, and then call double g and apply it to 0. So the result ends up being 2. Let's see. Well, maybe it's a better. This is a more interesting example here where we define the double function, and then we'll actually use it on a number here and a Boolean here. Okay, we'll kind of specialize it to two different types within the same program, and this example works as well. Okay. Okay, and it works because it infers a polymorphic type for double, and then if you recall, whenever it looks up double, it'll instantiate it with fresh type variables. So this double and this double don't necessarily have the same type. They don't have to have the same type because it's a polymorphic function. Okay, so I'm thinking of even though I've already given a lot of it away, I didn't show you the code for the unification algorithm, and there's still some more stuff. And so I might make this like an option for PA7. I don't know. To do something with this, I'm not sure. But we're about out of time. So, all right, no quiz. All right, so see you next week.